right, so let's take a look at the graph of f of x versus the graph of f prime. And you're going to have to go back and forth between these two. So if someone says, what is the derivative of f at point P, what are you going to say? You're going to say, because you know it so well, that is the slope of the tangent line at point P, okay? You could also say it's the slope of the function at point P, but I like saying the slope of the tangent line at point P. So what do you think if the derivative is positive? So if f prime is positive, what would f look like? Well, hopefully you would say, well, I could have something like that. It would be linear and all the slopes are positive, but would it necessarily have to be a line? Would it have to be a linear graph? No. It could be like this, because if you look at all the tangent lines on that piece, all my tangent lines are also positive. It could look like this. So what do all those have in common? Well, what those have in common is that f is going to be increasing. If the derivative is positive, then f will need to be increasing. And by that same token, you could probably answer the next question. So what would f look like if the derivative was negative? Then f is going to be decreasing. So I have several options. Yes, I could have that. I could have a decreasing function like that, a decreasing function like that, and the derivative would be negative. What does f look like when f prime is 0? And so most of the time people go, oh, that's the only case. But remember, we've had some 0 derivatives, and where was that? Remember how we had one like right here, where this, not on that whole piece, but right at that moment, the derivative was 0. Likewise, I could draw that. There's also another one that sometimes you don't think of, but it's a good one, because right here you have a 0, a horizontal tangent, and those are the words that is blanket statement for everything. If the derivative is 0, then f has a horizontal tangent. You're not exactly sure which one of those things it is, but the general statement that you can say is that f has a horizontal tangent. And based on what we said yesterday, what does f look like when f prime does not exist? Well, you could have lots of things. You could have that sharp turn where the right and left derivative aren't the same. You could have a vertical tangent right here. Or you could have any discontinuity because the derivative wouldn't exist there. So here's what I need you to see. We're going to graph on all these problems. This is the graph on the f. This is the graph of f, and this is the graph of f prime. So what you need to be thinking, and we're not going to get equations. I want you to understand it with just the idea of what a derivative is. If I drew tangent lines along this one, what do you notice about all those tangent lines? Okay, for one, they're all positive, so that means my graph of f prime is going to be above the x-axis. And aren't they the same? Like, isn't that tangent line? I mean, every single one of those I drew had the same slope. And what is that slope? You could actually figure out that that slope is 1. So that means at every x value, I have a slope at 1, so the derivative graph is going to look like that, and that's at a y value of 1. Let's try another one. Let's draw some tangent lines. So like at -1, approximately, there's the tangent line, so I know it's negative. Any tangent line, you know for sure what number it is. I can't really tell on that one exactly what number it is. Are there any points of that you know exactly what the tangent line is? And I hope you think of this one. Because right there you have a horizontal tangent. So that means when x is 1, the derivative is 0. So over here on the f prime graph, when x is 1, the derivative is 0. So I can put that point on my derivative graph. Now, what do you know about all the derivatives to the left of 1? Look at all of them. They're negative, so that means they're going to be below the x-axis on f prime. And what's happening? Well, way out here, these are really steep. That means they're very, very negative. Okay, like -10, -20. So they're getting more and more negative. As I get closer to 1, do you see how my tangent lines are getting flatter, which means they're getting close to 0? Now, I know you're going, well, how did you know that it's going to be a line? Again, trust me on this one. If you have a quadratic, the derivative is going to be linear. What happens after 1? They're very close to 0, and as I move away from 1, I'm getting steeper and steeper, so my derivative does this. You try to do number 3. Well, gosh, I hope that you see on number 3, well, wait a minute. If I drew the tangent lines, I'm getting the same tangent lines as I did on this graph. I mean, the f of x is shifted up, but at 1, I still have a derivative is 0, so I still have that dot. I've got the same tangent lines. These two derivative graphs are exactly the same. So notice that the derivative is not dependent on the y value of the original function because I have two different y values of these two graphs and their derivatives are exactly the same. In the same way, if I give you a derivative graph, you can't tell me the y values of f. You could tell me the general shape or what's going on, but you cannot draw the graph exactly with the y values. And so here's how I want you to look at this. Notice, as we said before, do you see here when the derivative is negative? Look at what f is doing. F is decreasing. When the derivative is positive, f is increasing. So that kind of goes with our statements we had before. And again, I'm not asking you to draw an accurate to scale drawing of the derivative. What I want is the basic shape. And I want the ones that you can tell for sure. The ones that you can tell for sure are when you have horizontal tangents. So this guy has a horizontal tangent at 0 and 2, which means the derivative is going to go through the x-axis at 0 and 2. Now, what do you think? I said a quadratic, so x squared, would have a derivative of x. So what do you think an x cubed, because that's what this is, x cubed is going to have a derivative of x squared. So my f prime graph is going to look like a quadratic. So I kind of know it's going to be parabolic. I just have to figure out which way. Well, finish this sentence. Right here, up until 0, f is increasing. What do we know? If f is increasing, is the derivative going to be positive or negative? Well, the derivative is going to be positive. And so, again, very, very much positive, and then it's getting closer to 0. Look in here, my function is decreasing, so the derivative is going to go negative. And then my function is increasing again, so my derivative is going positive. So I know if I knew it was going to be a quadratic, then it would have to look something like that. And that's all I would want you to graph right now. Okay, we'll get way more specific with it later on, but right now, that's all I want you to do. What about number 5? What's the derivative at every single one of these points? Draw the tangent line. Boom, boom, boom. It's horizontal. So this derivative graph is going to be right on the axis. So that's what you're going to be doing for some of it. Again, I really just want you, what I'm going to be looking for are the zeros of your derivative. That's what I'm going to be looking for because those are really the only definite points you can draw right now. Now this next question, boy, this is so AP-like. I've given you f primes. I have given you f prime, and I'm asking questions about f. Now what I like to do is I like to kind of tell my justification, because when this is on AP or one of my tests, not only am I just going to ask you for the answer, it's going to say the word justify. So I'm also going to write the justifications. So here's what you need to think about. At what x value does f have a horizontal tangent? Well, if you think of the justification, f has a horizontal tangent when what? When f prime, finish that statement, when f prime, and hopefully you said equals 0. Because if you think of that justification, if I say, hey guys, this is f prime, where is f prime equal to 0? You'd go, well, there and there. If you know what you're looking at and where to look, you're probably going to get the answer right. And that's why I like to write my justifications first. So finish this statement. On what intervals is f increasing? F increasing when f prime is positive. You can say it in words. So if you do is positive, if you say greater than 0, if you write out is positive in English, that's fine. So where is this graph? Where does it have positive y values? That's right there. So you say -4 to 0. And remember, increasing and decreasing, you always use the open brackets because you're talking about the interval. Okay? So I always use open. I've seen it with both, but I like open. You figure out C. F is decreasing when f prime, so I'll write this one this way just to show you the other option, when f prime is less than 0. So assuming these go on forever, f prime is less than 0 or has negatives there and there. So that would be from negative infinity to -4 and 0 to infinity. Now, where does f have a local maximum? And where does it have a local minimum? Well, think about this. Let's think about what that justification is going to be. When is f going to have a local maximum? A maximum is when you're doing this, when f is increasing and then it goes to decreasing. So if f is increasing and goes to decreasing, tell me what f prime would have to be doing. If f is increasing, f prime would have to be greater than 0. And then if f goes to decreasing, f prime would be less than 0. So the justification of this one is f has a local, and do write the word local because we will be more specific later with absolute, so get used to writing the word local. F has a local max when f prime changes positive to negative. Do not say when f prime equals 0. Am I saying that f prime equals 0 right here? Yes. But in that example like this, you have to do a justification that is true always. In this example, f prime is equal to 0, but it's not a maximum. So you will never, the f prime equaling 0 is for horizontal tangent and horizontal tangent only. You cannot justify a max or min that way. So where is the derivative changing positive to negative? It's going from a positive y value to a negative y value. Well, right there. So therefore, at x equals 0. And I bet you could now do letter E. because a minimum is when f is decreasing, then increasing. So f has a local min when f prime changes negative to positive. And where is that on this graph? That would be right there. And so that's at x equals -4. So start getting these relationships down, and you will be finding, doing some of the similar things, and we will go from there. All right, y'all have a good one. I hate it when I do that. What is